All right. So I have these two angles here, and I am asked to prove that they are the same size. Now, the way we're going to go about this is the way we've kind of gone about a lot of these things. We're going to start out by proving that two triangles are congruent, and then we're going to conclude, therefore, that specific parts, in this case angles, of those two triangles are congruent. So I'm going to kind of finish out my two triangles here. So here is one, and then down here is the other. Okay. Now, for our first two parts of this triangle, we've got that, let's see, AC is congruent to PR, and we could do and you really should do the Pythagorean theorem calculation and double check that, but that's the case. Next we got 1, 2, 3, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, 3. So we have CB being congruent to RQ. Okay. Again, Pythagorean theorem, you just find the lengths. I think these are, by the way, these are square root of 50, square root of 50, 36/9, right, is square root of 45, square root of 45, 1, 2, 3, 4, 5, 6, 7, 8, and 1. That's square root of 65, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 49, and 16 is also square root of 65. So then we have PQ being congruent to AB. Okay. So with all that in mind, these two triangles, triangle ABC, and then we have to be careful here, AB goes with PQ, ABC, so down the square root of 65 side, then down the square root of 45 side, so PQR. Right, so to make sure R is in between square root of 50 and square root of 45, C in between square root of 50 and square root of 45. So it looks like we named them correctly. So two triangles being congruent, therefore we can conclude that angle ABC is congruent, to angle ABC RQP. All right. And we could say, following that the measure of angle ABC equals the measure of angle RQP. Okay. So for the first three, in many proofs, you would just be given that kind of information. Here we just calculated it from Pythagorean theorem. Since all three sides from one triangle are congruent to three sides from the other, the two triangles are congruent by side, side, side. So knowing the three sides is enough to know that they're congruent. Once you know that they're congruent, we can say that particular corresponding parts of them are congruent. And so that means the two angles in question, that was, PQR and ABC, that those are congruent. Our reasoning is because corresponding parts of congruent triangles are congruent. CP, CTC, corresponding parts, congruent triangles are congruent. And then finally, we were specifically asked to say that the two angles were the same measure or the same size, and that's what congruence means. So we come down here and we say, well, measure of angle ABC equals measure of angle RQP, a definition of congruence. Right? So they're congruent, we concluded, because congruent parts of corresponding parts of congruent triangles are congruent, and to be congruent means that they're the same measure in this case. Right? Definition of congruence. Next up, we are asked, what if I had this point that was 3 units away, here and here, and I have a new triangle here and up here. By the way, I just sort of estimated where that 3 units was. And so now I've got these two triangles right here. So how can we go about proving that these two triangles are congruent? Okay. Well, first of all, we could say that that side, let's see, BD is congruent to side QT. So side BD is congruent to QT. Now we could, I suppose, go ahead, actually figure out the coordinates for point D are, figure out the coordinates for point T, calculate the distance between them. Hold on a second. But anyways, actually calculating those lengths is kind of doing a lot. Maybe it's doing too much, because if we know that that's 3 units, and we knew that AB was originally the same length as PQ, because that was an easy Pythagorean theorem calculation, well, whatever that length is, square root of 65, take away 3, is going to be, the same as square root of 5 take away, or square root of 65 take away 3 over here. So we can conclude using Pythagorean theorem, and I guess we could call it subtraction property of equality, that start out with equal amounts and subtract equal amounts, whatever you're left with is equal. And then of course we have that RQ, that is segment RQ up here, is congruent to BC. All right, we had that from earlier, and that's just Pythagorean theorem again. And then from an earlier proof, the one we just did, we have that angle RQT. We have angle RQT being congruent to angle DBC. DBC. Right? And we just proved that earlier, so we can use that proof in our new proof. Right? Use that fact in our new proof. So now we have RQ and CB being congruent, the angle here being congruent, and BC congruent to QT, so that's side, angle, side, side, angle, side. These two triangles are congruent by side, angle, side. Let's make sure we name them correctly. So that would be RQT triangle. All right, so if I go RQT, so it's down the 45, square root of 45, and then around the angle, so it'd be CBD going in the same direction. Triangle CBD. Okay. So, so the gist of the first proof again, if you know that the two triangles are congruent, you can then use that information to prove that particular parts, corresponding parts of the two triangles are congruent. And so that's what we did in the first proof, and we used side, 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 pretty common in a coordinate plane situation like this. But remember that corresponding parts of congruent triangles are congruent. That's our reason for knowing that particular corresponding parts that match up are congruent. And then we went that extra step to say definition of congruence means that the two angles are equal measures. Okay, so what do we mean that they're congruent? We mean they have equal measures. And then over here, we could take our earlier proof conclusion about the two angles and put that in here to say that the two smaller triangles are also congruent. Again, well, this time I guess by side, angle, side.